Hello, everyone, and welcome to this webinar organized by the Energy-Oriented Center of Excellence, a project funded by the European Commission. Today, José Fonseca, a postdoc researcher from CEA Maison de la Simulation, will present the algorithmic approach used to perform a Parflow+p4est coupling, as well as our latest efforts to generalize Parflow's native discretization to the locally refined meshes obtained with p4est. Thank you for joining us, and I hope you will find this very interesting. Jose, I'll give you the floor.
Okay, thank you, Julian, for the introduction. So let's get started now. So my name is Jose Fonseca. Yeah, I work at Maison de la Simulation, and yeah, my main task is to get to work this coupling between Parflow and p4est. So the layout of my talk is the following. I just give a short introduction, talk about the previous work I did already in this coupling, and I finish with what I'm currently doing now. So to introduce the problem, well, just to say that the accurate simulation of variably saturated flow in a porous media is really important in addressing many water resources problems. A common approach to simulate this kind of flow is to compute a numerical solution of the three-dimensional Richards equations, which I put a variant of them here. So P stands for the pressure head, and this K here stands for a conductivity tensor, and this is a parabolic time-dependent PDE, and it is a challenging task to solve this PDE because the nonlinearity and the large variation in the equation coefficients introduced by the conductivity tensor, and because of the requirement of high resolution spatial and temporal discretizations. So the efficient employment of high performance computing is a critical point. Just to give you a motivation how extensive these computations might be, this is a contour plot from a simulation run from an experiment in which you have a box with, say, sand, and you just let water flow down driven by gravity. A really fine resolution, and in order to produce this picture, then we produce 10 to the power of 8 and the magnitude of degrees of freedom, and did 17 hours of compute time using 16,000 MPa ranks, and this simulated only 9.8 seconds in real life time. So what is the simulation platform Parflow? So it is an integrated parallel watershed model which simulates surface and subsurface flow. It is based on this approach of solving Richards equation, which is solved using a cell-centered finite difference discretization. The code is rather old. We started the developments in the early 90s, and it has more than 100,000 lines of C code and a couple of Fortran modules for other functionalities. It is built using distributed parallelism, and it's suitable for large-scale simulations, and has shown excellent solver scalability for up to 16,000 processes, reported, for example, in the two references I put below the slide. So I worked previously with this code, and coupling it with this library with p4est. So let me just quickly say what is the p4est library, software library. It is basically an adaptive mesh refinement package based on the idea that a refinement scheme might be encoded by the tree structure, in which the leaves of the tree represent the elements of a mesh, and then a space filling curve is runs away this tree, and it defines a total ordering of these elements, as you can see to the right. When I change the mesh, how this translates into tree and back and forth. So what this library does is it basically exploits a lot of nice properties these space filling curves have in order to implement fast algorithms for sorting and searching, and for doing mesh partitioning and parallel mesh adaptation and parallel partitioning. I started like working in this coupling these two libraries when I was a PhD student in Germany, and in order to do that, I have to quite go really deep into the Parflow's way of parallelizing the code. So I put this here as a summary of what I have learned. As many PDE-based solvers, the parallelization of the code depends on the parallelization of the mesh. Parflow splits the computational grid into non-overlapping blocks, which are called subgrids. Each subgrid is assigned to a unique process in a parallel machine. And these subgrids and the processes are logically arranged in a lexicographical ordering. So the main idea, when I was a PhD student, it was like, and you have this tree structure from p4est, and then you have the possibility to put whatever you like on the leaves of the tree. So what we did is we place Parflow subgrids, choosing carefully in order that at the end you get a grid equivalent to the one you will get if you just use Parflow as a standalone version. This proved to be quite challenging, but we managed to succeed with it and obtain a code which is backwards compatible with the upstream version of Parflow. The user decides in runtime via configuration script if he or she wants to use p4est, and the code with these changes showed improved parallel scalability. And like here are a couple of plots. And to the left, I'm displaying back at that time in 2018 a quick scaling plot of the three main components of a typical Parflow simulation, and I discovered that the code was not scaling good. So after adding this after coupling with p4est, most of the bottlenecks causing this bad behavior were gone. And yeah, back then we got nice results. For example, we were able to use the full size of the current supercomputing in Jülich Supercomputing Center at that time. And yes, this is basically a summary of the code. So if you're interested in like, give it a try. These developments have not been yet merged into the main branch of Parflow. If you want to check at them, then you have to go to the GitHub repository from Parflow and check out the branch adaptive, and just follow the instructions on the subdirectory, which I call p4est wrap there. And if you are familiar with Parflow, basically the only thing you have to know is to add 3 more parameters into the TCL file specifying the problem in a typical Parflow simulation. So basically the topology key values are ignored when p4est is used as a mesh manager, and given the MPI size, the process partition is internally managed by p4est. And if the user should generate its own internal database file, I think this is a little bit like really Parflow-oriented users slide. And this is how it will look like in a typical TCL file. So you see here this new pair of case, and with p4est enabled, then the user has to decide how big wants these subgrids to be, as opposed to when you don't use it, or when you use the normal observation or Parflow, the Parflow will decide it's for you. So now we can move on actually what I'm currently doing in the framework of the EoCoE project. And it's basically a continuation of what I started before. So the main goal is to actually activate p4est AMR functionalities, because in all the plots and all the results I got before, it was all restricted to uniform meshes. So you remember that our idea was to place Parflow subgrids into the leaves of the p4est structure in order to get a mesh that Parflow can work with. So now the idea is that if I refine the p4est mesh using the p4est bundle of functions, then I should get another locally refined mesh in p4est. And this has proven to be quite challenging, because I discovered that Parflow has its own octree structure, which is used to loop over faces of a domain or to depict more complex geometries. And so the first step was to try to put these two objects into the same level, like to communicate each other, or to. So I also discovered that most of the algorithms of the Parflow octree, which is used there internally, come from really nice document I put here below from Donald Meager from 1982, and basically then I have to go and reverse engineer the code in Parflow, in which well, basically an octree is in a standard way created. And for example, here you want to represent the object depicted here, like shaded, and you just put it into a big box, and then you refine the box until the object, until all the leaves of that you get from refining that box, these simple leaves of boxes are completely contained into the object you want to represent. And then the tree representation, you just flag these leaves from the original one as empty, or if they don't intersect it, or flag it as P if they have intersection but that is not completely contained, and then repeat the same procedure until the small boxes here are completely contained in your object. So this kind of structure here is used to efficiently loop over faces, and for example, you don't have to loop over when you're looping. You can safely ignore all these empty guys here and just go over the elements which have actually are children. But and this is reflected into the code in Parflow. You find these kind of loops like really frequently in the loop, and there is inherently into this structure a level, which is I'm displaying you see my pointer here. But in the practice, in the observation of Parflow, this is practically R is always 0. So this you are not using actually full potential of this octree structure. So what I have to do is to tweak these loops and the Parflow's octree creation to take into account p4est's own octree convention, which is completely different. This was quite some work, but I managed to do it without disrupting too much into the Parflow original code. So basically what I make sure is that all the loops work correctly when I use a locally refined mesh with easy tests. But I can move on to the next issue. Now, of course, if you use a locally refined mesh, like in a finite difference setting, then there will be subgrids which are located in different processes, and they need to communicate in order to complete their computations. So this is solved in the finite difference community, or like by using an additional halo of optic degrees of freedom, which are called gold cells. And of course, if suddenly I change the picture in A by something that looks in B, like please ignore all these arrows, then I might face a situation in which if I leave everything and change the code, we'll be trying to send messages to the ground location, or for instance, these two subgrids here will send two messages to this big one here, and he does not have the space to get the message. There is no allocation for that. So we have to correct this. And what I came up is the following idea. So whenever I face a situation in which a coarse element, a coarse subgrid needs information from two neighboring subgrids which are smaller, then I kind of artificially create the children of the coarser guy and use them to perform the communications. So, for example, here in this small one in the top left one, then he will send a message with its own values to an artificially what I call inner ghost children, and then the processor owning the coarser subgrid has to do some pre-processing, like taking those values and probably doing some kind of restriction operator to put it on the ghost layer of the coarser guy. And the other way around, then the coarser guy will send messages to the two small subgrids, and before sending this message with MPI, I probably should perform some kind of interpolation to get the right scaling here, or that they live in the right real space, let's say. So I also have done this in the sense. Okay, there is some point that is really important to clarify. This is the only situation we have to take care of, because with p4est I'm enforcing 2-to-1 refinement meshes, which means that this is the only relevant case. Of course, in 2D, the picture, in 3D, then the picture is a little bit different, but for explanation, this is enough. So basically, then in a 2D situation, when I create the grid in Parflow, let's say I create this grid here, and in S stands for a subgrid, then a coarse subgrid should know if it has smaller subgrids, and then it will allocate these two smaller inner children here, and of course only in the cases if you need them. So with all the information you get from p4est, this is possible. Another point is that then, and this is related with this restriction on interpolation operators before, is that you have to extend the numerical scheme now, the finite difference scheme, in order to account for local refinement. There are some works like related to this issue, like for example from Ming, Yiwu, and Zenit Zeros, in which they use they have a really nice result there, in which basically they notice that you might be able to recover the right approximations properties of a finite difference approximation if you kind of tweak tweak it properly. So for example, in a 2D situation, let's say you're interested in approximating the Laplacian at the point P3, and this is what the information what you got is what is put it in the dot and the black dots. So I would like to use a standard 5-point approximation. So I would like to use for the x derivative, I would like to use this P in red point here together with P4, and for the y approximation, the top and the bottom, but this doesn't exist. So I interpolated using the available values. If I do it in that way and then do a standard Taylor analysis, then I will discover that this approximation of L defined in this way will approximate this operator here, which is not exactly the Laplacian, and the Ly will approximate this operator here, which is also not exactly the Laplacian. There is a factor here, which is which we have to cancel out, but we just have to weight accordingly these two expressions, and for example, just like it's done here below, then you will get actually an approximation of the Laplacian, which is first order accurate, and it reduced to a second order accurate if the mesh is locally is locally uniform. And this is the theoretical justification of this fact is you can find it here in this paper. So what I also done is, like, of course, for Parflow, I have to do this in a 3D setting, but it's completely analogous. And yeah, I have been checking all the different cases that might arise and in a 3D setting in order to write down or hard code like what is the exactly weighting that you might need to regain the right approximation of your tweaked finite difference. So this is an example. I run the code. You can solve the Laplace equation in Parflow. You just need to basically set up the order parameters in a intelligent way, and then it will Richard's equation will reduce to Laplace equation. So I'm using this to test everything I'm doing now, or like a starting point. And for example, here I'm just solving Laplace equation with this target manufactured solution to the left in a standard uniform grid. And to the right, I repeat the calculation using a randomly refined mesh, allowing up to 3 levels of refinement, if you might see here. And yeah, I'm getting the right thing. So I'm really happy about that, and I'm continuing to extend this because we want to solve Richard's equation and not Laplace, so we have to tweak the interpolation such that the other parameters appearing in the equation are also interpolated suitably, like for example, the conductivity. We also, of course, this will change the Jacobian of the nonlinear iteration. I'm tweaking it. It would basically add new terms. Yeah, the reason I'm not trying to solve Richard's equation or doing a more realistic simulation is that because we don't have preconditioner. The ones which are coded in Parflow don't like now that we have refinement meshes. So I will choose one and try to extend it accordingly. The most likely is the self-coded preconditioner in Parflow, which is called MG-semi, because it's coded inside there. It does not depend on external packages like the other preconditioners that are relied in Hypre. And the last point, as you learned from the last webinar, there is a GPU implementation branch which has OpenMP capabilities, and this as soon as this GPU branch is merged into the master, it would be really interesting to merge it back into this adaptive branch to take advantage of the OpenMP implementation. Because I did not mention that before, but in the adaptive branch, you have the couple of advantages, and one of them is that you might use more than one of these subgrids per process. So I think that can be nicely combined with now the OpenMP implementation to experiment with some hybrid parallelization. And yeah, that's it. That's basically I've been doing, and I really thank you for your attention.
Thank you, Jose. We are now moving on to the question and answer session of this webinar. If you have any questions about what's just been said, please use the ask question or raised hand function of the GoToWebinar application, and I will open up your mic so you can speak. Okay, I have a question from Mathieu Effeli. Mathieu, please go ahead.
Yes, hello, Jose. So nice to hear from you. I have a question regarding to your last slides about OpenMP. So it's linked to the GPU implementation, and so I guess the OpenMP used here is using the target OpenMP target primitive, right? And how would you? So the idea is to bring the adaptive mesh refinement technology on GPU, or is to use OpenMP implementation on CPU?
No, I was thinking more into using onto the CPU. In the GPU would be really difficult to use because the way in which p4est moves data, it would be really difficult to communicate this to the GPU.
Yeah, okay, that was also my feeling. But then on CPU, is the OpenMP implementation compatible with CPU?
This is something I like to investigate. I'm just like being like, I just saw this was available from the last talk, and I find it like I find it interesting to give it a try because I think so far no one has tried to do hybrid OpenMP MPI experiments with Parflow.
Yeah. Okay. Thanks, Matt.
Yeah.
Thank you, Mathieu. I'm opening the mic for Mr. Laurent Orgogoso. We can hear you. Mr. Orgogoso? Okay, we don't seem to be able to hear you. I'll move on to someone else and then I'll come back to you. Opening the mic from Mathieu Lobet.
Yes. Thank you, Jose, for this presentation. Maybe you could give more details to Mathieu Effeli about the OpenMP and your version of Parflow. First, to reply to Mathieu, so the GPU implementation is not using OpenMP target. It's only based on CUDA. So OpenMP here is only for the CPU part. The interesting thing in the work of Jose is that thanks to the multi-grid, I don't like to call it multi-grid, but the fact that now you could have multiple grids per parallel regions means that you could, for instance, have one MPI for a bunch of grids, and then using OpenMP to solve each grid on a separate thread. So what is currently doing Jose could end up improving the hybrid parallelism on CPU using MPI plus OpenMP. This is so far what I have understood from Jose.
Yeah, thank you. Yeah, that's a point. Yes. Thank you, Mathieu.
Mathieu Effeli, I'm opening your mic again if you have a reaction.
Yes, but so yet it's much clearer. Thanks a lot. Yeah, thanks.
Okay. Now trying again, Mr. Laurent Rogosso, raise his hand.
Hello, do you hear me?
Yes, we hear you.
Great. Hello, I'm Laurent Rogosso, hydrologist at Geoscience Environment Toulouse. And I was I was interested in a bit more detail about the large example case you shown in the beginning of your presentation. And I have also a question related to how do you expect the partition of the numerical efforts between computation itself and adaptive mesh refinement itself, being in simulation with such large meshes?
Yeah, so first, what would you like to know about the first picture? Do you mean this one here?
Yes. Is this, for example, is this random hydraulic conductivity properties, or is this homogeneous medium? Which kind of physics is dealt with in this example?
Yeah, we just generated a conductivity tensor using a random random field generator. I don't know if you're familiar with the turning bands algorithm.
Okay.
Yes, we just use that to generate a random field, which will require really fine resolution in order to depict the scales that you are seeing there.
Okay. So, and what is the space scale? Is this 100 of meters or kilometers or meters? Or?
It's a box of 50 times 50 meters in 6 meters depth.
Okay, thank you. And so when imagine you make AMR with this kind of large mesh, how do you think that the partition between the effort for production itself and the effort for adaptive mesh refinement process would be? 50-50, 10-90? What do you think about that?
Do you mean how much work relative to the computational work will take to actually adapt the mesh?
Yeah.
Well, the whole algorithmic approach using in p4est it makes these operations really cheap. We will have then to like actually refinement the mesh and redistributing it. It is really I don't know, but it's difficult to say a number, but it is a non-significant amount of time.
Okay.
But this is only from the p4est part, and then of course I have to think about that. Then, for example, if I'm doing this kind of refinement, then the post-processing I do with the, let's put it in this way. From the p4est point of view, doing all this kind of manipulation of the mesh is relatively cheap, and I don't think that it will take more than 10% of the running time. Only from p4est only functions. But we might have a little bit more of overhead, because then I have to take this information I get from p4est and propagate it into Parflow and then my grab code is doing some work as well. But I'm positive that this should not be that bad.
Okay, thank you.
Thank you. I'm opening the mic to Hugues Digonnet. Mr. Digonnet? Mr. Digonnet, I'm afraid we cannot hear you. I'll come back to you in a second. So now I'm opening the mic for Mr. Sean McGovern.
Oh, hi. Yeah, this is Sean McGovern. Can you hear me?
Yes, absolutely.
Oh, okay, great. Yeah, thanks, Jose. Yeah, so I'm down in Nice in Ria Sofia Antipolis, but I know Jose from Bonn. And I just wanted to clarify, so the work that you're doing currently, Jose, are you, is this over more than one time step, or is this kind of a static computation?
I'm still with the static computations.
Okay. Yeah.
Yes.
Okay, yeah, fair enough. And then I was just wondering if you could maybe say a little bit more detail on sort of where, so if I understood correctly that the nonlinear solver functions, but then you're running into issues with the preconditioner that you would like to use and can't. Is that accurate?
Yes.
Okay. I'm just curious, would you, maybe not in great detail or anything, but could you kind of point in the direction of where the preconditioner is not happy with AMR?
Basically, in the construction of the smoothing operators. I mean, the preconditioners are all of them multi-grid.
Right. Yeah.
And in Parflow, there are like currently 3 options to precondition. Okay, 4 if you don't precondition at all, but this is not an option. And 2 of them are multi-grid preconditioners coming from the Hyper package, and they just don't support adaptivity in the way that we do it with space filling curves. They like more patch based structure.
Okay, so Hyper is AMG, right? So
yes.
I don't know too much of the details, but I would just say that I know that, for example, the software library Deal2, uses p4est as well as Hyper AMG. I'm not sure the details of how they get it to work, but in principle, anyway.
Yeah, I
can play together.
That is because they in Deal2 they use the Boomer AMG, and this one does not care if you how the adaptivity is. But the preconditioners that use it into Parflow are called PFMG and SMAG, which actually come from Parflow originally, and they are not suitable for this kind of meshes.
Oh, interesting. Okay, and then I'll wrap up. But where does Boomer AMG fail in Parflow, or could that not be used?
You're not using Boomer AMG at all in Parflow. You're using.
But I'm just curious if it would be possible to use Boomer AMG in Parflow, or if there's a technical block there.
No, I think that is something that we can give a try as well.
Okay.
I don't see why not. It's just that the other option that you have in Parflow, which is called AMG semi, it's completely coded within in Parflow, and you don't have to. It's written in a really Parflow way with all the macros and all the this kind of DSL language there is embedded there.
Okay, yeah, I think that makes sense. Just like historically, I think people out in Berkeley were involved in both Hyper as well as development of Parflow. But okay, thanks very much. I'll cede the space and I'll let other people ask questions. Thanks, Jose.
Okay.
Okay, thank you. Trying to check if there's other questions. Yes, trying again for Mr. Hugues Digonnet.
Yes, you heard me or not?
Yes, we can hear you.
Okay, thank you. Well, I was disconnected a little just now, but what I want to ask is more about load balancing or unbalance, because as soon as you make some mesh adaptation in one, you can create some unbalance between cores. And do you deal with that, or p4est do this for you? I don't have seen anything about that.
No, not yet. We all this testing I've been doing is in a single time step, so it's practically statically refined. But regarding the load balance, p4est has a lot of it provides a lot of tools to do that, and basically what you have to take care is just to pass a kind of weighting function to p4est. Specifying which portions of the region have the important computations. So that
it was more on the number of grid points you have, because if you refine only on the top left part or something like this, you will create a lot of extra work on that part.
Yes.
And this may, so the core that that deal with that maybe much more heavy than others, and so you may create some very big imbalance between the works done by each course.
Yeah, yes, but the mesh is P4est allows you to do this kind of load balancing in a
Okay,
quite efficient way.
and you can go back this load balance to the software after that or not?
Sorry, could you repeat that question?
Because if P4est do that for you, okay, but in P4est format, can you go back to the software after that? Yes.
Yes, because we basically have built a bijection between the P4est object and the mesh in Parflow.
Okay.
So
Okay.
okay.
Sorry, do you have anything to add?
No, it's okay. Thank you.
Okay, thank you. Just checking one last time for the question, but I think we've gone through everyone. Yes, that's it for the question. Well, thank you all for attending this webinar. Jose, thank you again for hosting it. Just so you know, the entire recording of the session will be made available on the YouTube channel of the EoCoE project. You will receive a link to the webinar, and we will also make sure that you all receive a version of the slides that we use today. We will be planning future webinars for the months of September to December 2020, a bit later this summer. So we'll keep you in the loop regarding these future sessions. Thank you again, and have a nice day, everyone.